Hi, and welcome to the least squares estimation lecture as part of the regression course in the data science specialization. My name is Brian Caffa, and the course is co-taught by myself, Jeff Leake, and Roger Pang, and we're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Consider again when we're looking at the scatter plot of the parent's heights by the child's heights from the Galton data. Here, remember, the size of the circle represents the frequency of that particular XY combination. We'd like to use the parent's heights to explain the child's height, and we're going to do it using linear regression. We're going to use our notation that we developed in our last lecture. So let's let yi be the ith child's height and xi be the ith's parent's height. Now we want to find the best line, where we want the line to look like child's height is an intercept, which let's label beta naught, plus the parent's height times a slope, which we're going to label beta 1. So beta naught and beta 1 are parameters that we would like to know that we don't know. Well, we need a criteria for the term best. We need to figure out what we mean by the best line that fits the data. Well, one criteria is the famous least squares criteria. And the basic gist of the equation is we want to minimize the sum of the squared vertical distances between the data points, the heights of the data points, the child's heights, and the points on the line, on the fitted line. And we can write this as summation yi, the child's heights, minus beta naught plus beta 1 xi, where that particular parent's heights would put them on the fitted line. We'll go through this a lot, and hopefully you'll get the hang of it. And then later on at the end of the lecture, I'll actually show you the math of how we can come up with a solution for those that are interested. Let's talk about what our equations mean with a picture. Here's a data set. What our least squares criteria to find the best regression line is going to do is it's going to take each point. So for example, take this point right here. That's the point x1, y1, and this might be the point x2, y2, and this might be the point xn, yn. It's going to take all these points and fit a line through the data. Let's draw our line right here. It's going to fit a line through the data. And the way it's going to pick this line is it's going to take, for example, our x1, y1 point. It's going to calculate that distance. And that distance is y1, the height, that height, minus the point on the line. So this line, let's assume, has intercept beta naught. So beta naught is the height along the vertical axis, has intercept beta naught and slope beta 1. So that's the line that we're interested in. So this point right there is beta naught plus beta 1 x1. This distance then is subtracting the two, and because that can be either positive or negative, it would be negative in this case. We square it, and then we do that for every point on the line and add them up. So each point on the line contributes equally to the error between the line and the fitted points. Then we try to minimize that error, and that's what the least squares criteria is doing for us. So let's discuss what the answer is when you perform this model fit. So just to reiterate, we want the line y equal to beta naught plus beta 1x, and we're going to fit it through a scatter plot of points xi, yi, where yi is the outcome. We put little hats over beta naught and beta 1 to indicate the estimated values. The solution works out to be beta 1 hat is the correlation between y and x times the standard deviation of y divided by the standard deviation of x. The estimated intercept, beta naught hat, is y bar minus beta 1 hat times x bar. So let's go through a couple of consequences of this being the result. First of all, beta 1 hat has the units of y divided by the units of x. That's its units. So we can see this because the correlation is a unitless quantity. Standard deviation of y has the units of y, and standard deviation of x has the units of x. So because the line, remember, because the slope of a line is change in y divided by change in x, it has to have units of y divided by units of x units. Another important point is that the line always passes through the point x bar, y bar. We can see that from the equation for the intercept. If we rearrange it, we simply get y bar equals beta naught hat plus beta 1 hat x bar. So if we plug in x bar into our equation for our fitted line, we get y bar out, which means that the line has to pass through the point x bar, y bar. If we reverse the role of y and x and treat x as the outcome and y as the predictor, then we simply get the answer that the slope of this line is the correlation times the standard deviation of x divided by the standard deviation of y. So you get a different answer, of course, when you fit x as the outcome and y as the predictor than if you fit y as the outcome and x as the predictor. The slope is the same if you were to center the data first. In other words, take each xi and subtract off its average, take each yi and subtract off its average, so that now the origin is exactly the mean of the data. And if you were to do regression forcing the line through the origin, you get the same answer. I would also note that if you normalize the data, don't just center it, but center it and scale it, the slope is exactly the correlation, because the standard deviation of the x variable is 1, the standard deviation of the y variable is 1, and so we can see just from the correlation, just from the equation for the slope, that it'll just be the correlation. So I wanted to show you the slides that I was working on now, the actual R Markdown file. So this is the .rmd file. And first I want to plot the data that I'm going to look at. This is the Galton's parents' height and children's height data. So I'm going to plot it here using ggplot, and there's my plot. Now I'd like to go with the information that is on the slide, which is some R code. So I thought it'd be probably better to just show you the running of the R code rather than showing you a slide with the output of having run the R code. So here for convenience, I've defined my outcome as the child's heights, Galton $child. So let me define those. And I've defined the X, the predictors, as the parent's height, Galton $parent. And this is just going to save me on some typing. Now first I'd like to indicate that the solution that we specified is the same solution that R will give you with its built-in regression function. So here's beta 1. It's the correlation between y and x times the standard deviation of y divided by the standard deviation of x. And here's my beta naught, which is the mean of y minus the beta 1 that I just estimated times the mean of x. So I can, for example, look at these with beta 0 and beta 1 in this C function for just creating a vector. Let me check that with the LM function. I'm going to copy the function and paste it down here, and then I'll go through each of the components. LM in R stands for linear models. Regression is a component of linear models, and so this function is the general function whether you want regression or you want some of the more elaborate versions of regression that we're going to cover later on in the class. So we want LM, the outcome y, tilde, the predictor x, and that does a linear regression. By default, it includes an intercept. Coef takes the output of the linear model and just grabs the coefficients. And of course you see that we get the same numbers, 23.94 and 0.65. Very briefly now, I just want to show you that if I reverse the y and x relationship, the formula of course holds, but now with standard deviation of x in the numerator and standard deviation of y in the denominator. So I'm going to now define my beta 1 as correlation of y and x, but now with standard deviation of x in the numerator and standard deviation of y in the denominator. My intercept is now mean of x minus beta 1 times the mean of y. Now I'm simply going to concatenate these slope and intercept estimates with those that you get with LM, where now x is on the left-hand side of the tilde and y is on the right-hand side of the tilde, reversed from what it was previously. And there, of course, down here you see that you get the same numbers. So our formula is correct, and we know how to use it, and we know what happens when we reverse the xy relationship. Another point that was made thus far in the lecture was that regression to the origin yielded the same slope as linear regression with a not necessarily zero intercept if you mean-centered the y's and mean-centered the x's first. So let's just check that computationally. My centered y is just going to be y minus the mean of y. My centered x is just going to be x minus the mean of x. And recall that the regression to the origin equation for the slope was just the sum of the y variable times the x variable divided by the sum of the x variable squared. So let's run that and get our coefficient that is estimated through regression to the origin. And then now what I'm going to do is I'm going to take this beta 1 that I got through my equation for regression to the origin, where I've mean-centered my data first, and then I'm going to compare it to the linear regression estimate using LM with y tilde x, meaning y is my outcome, x is my response, and LM automatically puts in an intercept, and I'm going to grab the second coefficient, which is the slope. When I do that, if you look down here, you see, of course, that you get the same numbers. I want to very briefly also just show you how you can actually do regression to the origin using LM, how you get rid of the intercept. So in this case, I'll get the same number if I take the centered y and use the centered x as a predictor, but I want to subtract out the intercept. So you put a -1 to get rid of the intercept. And you'll see here, 0.6463, you get the same slope estimate. Another point that was made in the lecture was that if we were to normalize the y's or the x's so that they have standard deviation 1, the slope would be the correlation. So let's just double check that really quickly. Here I'm normalizing my child's heights by subtracting off the mean and dividing by the standard deviation. Let me just double check that these now have standard deviation 1. There you go. And I'm going to do the same thing for my x variables now. So now both my y and my x variable, the yn and xn variables, can be interpreted as standard deviations from the mean in the y's case for the child's heights and in the x's case for the parent's heights. So we've gotten rid of the original units, the inches, and now they're in standard deviations from the mean. Now I simply want to show with this concatenation operator here that the correlation between the original y and the original x is the same as the correlation when I normalize the y and I normalize the x, and it's the same as the coefficient for the linear regression when I fit the normalized y as the outcome and the normalized x as the predictor. And when I run it, if you go down here, of course you see that all three numbers are the same. The last thing I'd like to do is simply show how to add a regression line to a GG2 scatter plot. Here over on the right, I'm showing this somewhat fancy plot I've been giving for this data, where the sizes of the circles are the number of parents and childs at that specific XY location. And the color of the circle is also representative of the frequency. I've defined over here my aesthetic so that X is parent and Y is child. And if you want to add a linear regression line to this point, you simply take your plot, which I've assigned to the variable g, and you want to add geom_smooth. You want to use the method as LM, and you want to give it the formula y tilde x. If you omit the formula, it's going to assume that the formula is y tilde x. So let's add that layer to our GG plot, and then let's replot it. And there you see the regression line overlaid on top of my scatter plot. I would also note that ggplot2 does a very good thing for us on our behalf, is they automatically give us a confidence interval around the line. We'll talk about how to generate this confidence interval later on in the lecture, but it's very nice that they're thinking of statistical uncertainty automatically. The last thing I'd like to do is to demonstrate that the linear regression slope estimate is beta 1 hat equal to the correlation between y and x times the standard deviation of y divided by the standard deviation of x. I'd like to demonstrate that. It's going to take some doing, and if you don't want to get this involved in the mathematics, now would be the good time to stop the lecture and move on to the next one. However, if you are interested, again, I'm going to do this in a way that doesn't require advanced mathematics, but you have to be familiar with mathematical notation and pretty comfortable with it. So before I do full regression, let me do regression through the origin. I'm going to draw this line here. So I want to fit the best line y equal to x beta through my data. My data is y1 up to yn and x1 up to xn. I would like then to minimize the criteria summation yi minus xi beta squared, where the sum is from I equal 1 to n. Let me let beta hat be the solution, and we'll see what has to happen about that solution to make it work. So this equation here is equal to the summation I equal 1 to n yi minus xi beta hat plus xi beta hat, simply because I've just added 0 minus xi beta squared. All I've done is add 0. I can expand this square, summation I equal 1 to n, yi minus xi beta hat squared, and I'm going to distribute my sum, minus twice summation I equal 1 to n, yi minus xi beta hat times xi beta hat minus xi beta plus the summation xi beta hat minus xi beta squared. Now, if I get rid of this term, it's adding up a bunch of positive things. I'll only get smaller because I'll have thrown away something that's positive. So if I take 6, which is 4 plus 2, and throw away the 2, I've gotten smaller. Okay, let's look at this term right here. If beta hat forces this term to be 0, then let me just rewrite this. If it's 0, I will get the following. I'll get that my least squares criteria for any beta is larger than what I get when I plug in beta hat specifically. So that beta hat would have to be the minimizer, because every other beta is it creates a least squares criteria at least as large or larger. So if we can make this term 0, then we've found our estimate. So I want to solve summation I equal 1 to n yi minus xi beta hat xi times beta hat minus beta. I would like to solve that equal to 0. This term does not depend on I, so I could divide it from both sides of the equation and it would simply go away. Solving this equation for beta hat yields the solution summation I equal 1 to n yi xi divided by summation xi squared, I equal 1 to n. So that yields our beta hat for regression through the origin. Let's consider an example that we've already shown otherwise. So imagine if x1 all the way up to xn are all equal to 1. Then my equation, where I want to minimize summation yi minus xi beta, my regression to the origin equation works out to be summation yi minus beta quantity squared. It's mean-only regression. Our result says that beta hat for regression to the origin in this case is summation yi xi divided by summation xi squared, which in this case is summation yi divided by summation xi squared. Xi is 1, so 1 squared is 1. And if I add them up, I get n, so it's y bar. Simply reiterating our proof earlier that y bar is the solution to the least squares criteria for mean-only regression. So let's consider general linear regression. Here's our equation for our line, and here's the least squares criteria that we would like to obtain. We'd like to find the beta naught and beta 1 that minimize that equation. Our work already is going to make this very easy. Imagine for the moment that beta 1 is fixed and known. Then I'm simply going to rewrite this equation as summation I equal 1 to n yi minus beta 1 xi minus beta naught quantity squared. And then I'm going to write that as summation I equal 1 to n y star minus beta naught squared, where y star is equal to yi minus beta 1 xi. We know the least squares solution to this equation. It has to be, the solution has to be, beta naught has to be equal to the average. I forgot my I subscript there, so why don't I put it right there and right there. Has to be the average of the yi stars. Let's plug back in what yi star is. It's summation yi minus beta 1 xi divided by n. If I distribute out that sum, I get y bar minus beta 1 x bar. So my least squares criteria is only going to get smaller if I plug in a beta naught that satisfies y bar minus beta 1 x bar. So why don't I do that? And I get summation I equal 1 to n yi, and now I'm simply going to plug in my new beta naught, because I know that whatever solution beta naught and beta 1 are, they have to follow this relationship, which is again saying that the fitted regression line has to go through the average of the y's and the average of the x's. So it's yi minus the beta naught that I just solved for, y bar minus beta 1 x bar minus beta 1 xi. So we know our solution has to do that. Now, this is equal to summation I equal 1 to n yi minus y bar minus xi minus x bar times beta 1 squared. And I forgot my square right there. Now, and I'm going to put some parentheses here, I'm going to rewrite this again. This is summation I equal 1 to n y tilde minus x tilde I, in both cases, times beta 1 squared. This is exactly regression to the origin, where now my outcome is y tilde and my predictor is x tilde, where yi tilde is equal to the centered y's, yi minus y bar, and my xi tilde is equal to the centered x's, xi minus x bar. Well, we know what the least squares estimate for this equation is. The beta 1 hat has to be summation yi tilde times xi tilde divided by summation xi tilde squared. Let's just plug in what yi tilde and xi tilde are. That's summation yi minus y bar times xi minus x bar divided by summation xi minus x bar squared. Thus, I can divide both sides by n minus 1, the numerator, both the numerator and the denominator by n minus 1. And this works out to be the covariance between y and x divided by the variance of x, which I can write as the correlation between y and x times the standard deviation of y over the standard deviation of x. So my beta 1 hat has to be this, the formula that we gave. Then my beta naught hat is given above as y bar minus beta 1 hat x bar